Hello everyone, my name is Adrian and I'm the characterization lead of the Hydro DOE senior design team with sponsors of Department of Energy and industry contact of Hydro. And today I will be talking with you about our recycled cast aluminum alloy development project. So a little background on this project: recycled aluminum produces significantly less CO2 equivalent than primary aluminum and steel. As you can see, from primary aluminum to secondary aluminum, there is about a 96% reduction in tons of CO2e per cubic meter. This is very important because it shows secondary aluminum is much more cost and energy efficient. And this is primarily because secondary aluminum has a much smaller production process than primary aluminum. Additionally, the electrolysis step in primary aluminum production produces a significant amount of CO2 equivalent per cubic meter. As you can see, it's all over 30 tons of CO2e per cubic meter, while the entire process of secondary production only produces less than 10 tons of CO2e per cubic meter. So it is much more energy efficient. So in order to utilize the secondary aluminum, it has to be sorted from mixed end-of-life scrap. First, this mixed end-of-life scrap goes through a variety of different separation techniques, such as magnetic separation and eddy current separation, and this separates out the ferrous and the non-metallic portions of the scrap, which then goes into Zorba, which is known as the non-ferrous portion of the end-of-life scrap, which is further separated via sink float separation into Twitch, which is our aluminum portion of this end-of-life scrap, Zorba, and trace elements such as brass, copper, or zinc. So this twitch is then broken down using LIBS, which is laser-induced breakdown spectroscopy, into the wrought portion and the cast portion of the alloy. The wrought portion, which makes up about 20% of the twitch, is usually sold back to companies like Hydro, where they will then put it back into their products and reuse it. While the cast portion, which makes up about 80%, is usually downcycled into lower value alloys. Our project focuses on finding a use and enhancing these cast portions of Twitch into higher value alloys. So from the 300 series that comes out of Twitch, most of it's either 319 or a 380. And for our base alloy for this project, we chose 319 since it is heat treatable and can be made via a permanent mold, which is what we have at our Michigan Tech facilities. In order to maximize this 319, we have to find a way to maximize its toughness values, its ultimate tensile strength values, and its elongation values, which will make it a good structural alloy. By doing research, we found that cerium additions up to 0.5 weight% can increase elongation in aluminum, silicon, magnesium alloys, and nickel additions in aluminum, copper, iron alloys help spheritize and beryllium phases and will increase the strength. So our hypothesis is that if we can add nickel and cerium additions into our 319 AL scrap alloy and peak age it, then the elongation and the strength will increase to make it a desirable structural alloy. And this is because the nickel and the cerium will change the morphology of the brittle aluminum iron phases and turn them into rounder spheroidized structures. We made a DOE based on this hypothesis, where we had 5 different samples with varying compositions of cerium and nickel, and we tested those via tensile testing to find the elongation and ultimate tensile strength values. Based on our test results, the 319 base alloy gave the highest UTS, while the high cerium low nickel alloy gave the best elongation. Additionally, we did hardness tests on our samples, and we found that with additions of nickel and cerium, that correlated to decreased strength of 319 alloy. Additionally, we did SEM, which is scanning electron microscopy, to determine what the composition of the phases were in the alloy's microstructure. And from that, we saw that cerium additions added plate-like phases and nickel added blocky ribcage-shaped phases. In the future, for this project, we plan on doing additional mechanical testing and plan on doing fracture analysis of our tensile samples. From those results, we plan on developing a new DOE for further analysis. We would like to thank all our sponsors and those who helped us in this project, including the U.S. Department of Energy, Hydro, Michigan Tech staff and faculty, and Dave Weiss, who all contributed greatly to our project. Thank you.